We're in Module 4 again, the novice problems, and we're looking at solutions 3 and 4. These are going to be problems in regression and using the chi-square test of independence for categorical variables. Let's look at our problem. We've got a problem here where we've got a product X that sells, and it affects sales, services, and accessories for that product. And we're trying to determine from the sales of X what will happen to Y. The dependent variable is Y, the independent variable is X. So we'd like to be able to predict what sales, services, and accessories are going to be as a result of a direct sale. We've got 78 values over time. Each observation represents a combination of a X and a resulting Y. The way to get a regression formula is to engage the Data tab. Of course, you can do this also in Minitab. Go to Data Analysis. Down at the bottom, there's something called regression. Let's get rid of what's in here now. Let's grab our X or Y variable, including the label. This is our dependent variable. Now let's grab our X variable. This is our independent variable. I've got labels. I want the residuals. I want standardized residuals. Let me get rid of these plots for now because they do get in the way. If I locate where I want the output to go, which should be right here, let's say. I hit OK. And here's our data on the regression analysis. We can see that what we've got is a R squared, an adjusted R squared of 0.6, an R squared of 0.77. Usually you report, of 0.6. Usually report these two numbers in regression analysis. It tells us a percent of the variation that occurs in Y as a result of X. We also have the coefficients of the regression. Here is the constant, and here is the slope associated with X. We also have some other numbers. There's something called the significance F. We're going to need that in just a second. We're also going to need this value that you see here, which is the standard error. So let's go back to our problem for a second. First thing we want to know is to specify the regression formula. Well, the regression formula and the R squared. The regression formula is simply those constants that we got, the intercept constant and the slope. Here's our slope, 4.236 times X. Here's our constant, intercept constant. The next question that is asked for is, by the way, the R squareds are provided up here also. Here's our R squared and adjusted R squared. With simple regression with one variable, usually just report the R square, not the adjusted R square. We also want the variability of the observed Y values from the predicted Y values, and that is really something called the standard error. Here's our standard error. There goes our answer. The next thing we ask is the slope that we've calculated here from the regression, is it significant? In other words, does it really matter? Or could I have just set it to 0? The way we make this determination is we look at this value, the significance F. This is just like a P value from before. And you can see that this P is very, very small because there are, I'm going to go over 17 positions to the left to put the decimal point. This is going to be a tiny, tiny number. And we compare this number to our alpha value, which is 0.05. If P value here, if significance F, which is a form of P, is less than our alpha value, then it is significant. So it is not 0, it is significant. The last thing we want to do is we want to take a look at the values that might be outliers. And so we've decided that outliers are going to be anything that has a standardized residual. Standardized residual is a form of residual that's calculated. that is greater than 2. And we find one here, find one here, one here, one here. If we were to take these values out, we would get a very different, likely a very different regression formula as a result of that. So we may want to throw those out if we don't believe that they were representative of the real data. Okay, so that's the information that we need. By the way, here's the where we record the observations that are residuals that are outliers. These are the various observations. Let's go to problem 4. In problem 4, what we've got is a problem that relates to categorical data. I am interested in determining whether or not there is a relationship between gender and the type of coffee that an individual drinks, either woman or man. And so what I've done is I've collected data. I want to see if if these two variables are independent, gender and the type of coffee that is had, coffee drink that's had, or if men are more likely to drink one kind of thing and women are more likely to drink something else. So over a period of time, I collect observations. There are 60 observations, and this is the joint outcome of what happened. This was a male, drank coffee. Here's a female that drank coffee, etc. So I have all of these groups here, and in order to do a count of all the males that had coffee, for example, I'm going to have to do some sorting, and the sort keys are going to be gender first and drink second. So I've sorted this data. I've got 6 observations that are female cappuccino, 7 that are female coffee, female latte, female soy, male cappuccino, etc. And so these are the numbers that I want. These are the counts that I get of these categorical circumstances of a male and coffee, for example. I had 18 occurrences of that. So I'll take that data that I saw a little while ago, calculated from that sort, and I'll place it in my table. This is called a contingency table. The next thing I do is I create an expected value table. I've already done that, and I will do that for you on an exam, so you don't have to worry. You simply place these values here in this table, and the expected values will show up in the expected value table. The next question that has to be answered is, all right, can I calculate a chi-square? That's the statistic that's of importance here. And I can calculate that chi-square by summing the variations, the squared variations of the expected versus the observed values, and I get a chi-square. That doesn't mean much to us. What's more important, just and like in a lot of our other observation, is a p-value. I can calculate a p-value by using this chi-test function that specifies both the actual range and the expected range. The actual is the observed values. The expected is here. I just give it that information, and it calculates a p-value. And we can see that this p-value is 0.013591, which is less than 0.05. So the rule is the same as it was before in hypothesis testing. As a matter of fact, this is a test of hypothesis. So if my p-value is lower than my alpha, I reject the null hypothesis. Invariably, the null hypothesis in these tests is that there is independence. There's no dependence between male and the type of coffee that's had, or female and the type of coffee that's had. So what we've proven here is that there is a dependence, that they are dependent. I'm going to reject the null, that they're not independent, in favor of yes, there is an independence. You can kind of see that from the data. We've got, of the 32 individuals in the male set, 18 of them had coffee. That's a very large proportion relative to the females that had coffee, for a relatively similar number, 28. These numbers don't have to be equal to one another, the samples of males and females. So there does appear to be a dependence on the type of coffee drink that is had by a male or a female. Women in particular look like they're more egalitarian in their choice of drinks. Men just seem to prefer coffee. I forget where I got this information, but I think it's real information. All right, thank you very much. That's the end of our problems 3 and 4 for Module 4.